So talk about hero for tree per se, and obvious that we actually got to start establishing everything before we actually kind of like move on per se. So uh, the hero that we are playing with today is tree per se, and uh, we're talking about specifically a binary search tree, and obviously we always use brute force to actually argue against like why use tree per se. And for conditions, there's obviously the after conditions to consider for, and um, um, for the most parts is that we're gonna be on the playout series honestly because we are very uncomfortable with the topic per se. All the more we should have the playout series, and this is one of the more complicated ones, I would say. I mean, the core objective of this is that for this is to actually efficiently insert the values, remove the values. That's what we're actually doing. So inserting, we have uh, removing per se, and usually for all this I think it's log n times big O time complexity. So we're gonna try to actually figure out um, and do the playout series. So they're talking about like there's like two cases that makes they mentioned that remove is one of the more complicated one because there's a lot of like moving parts that's going on, and we're gonna like see during the playout series why do they actually say that. So for this one I think that we're actually highlighting right now, it's actually case 2 where there's actually two children, which makes things really really complicated. For case 1 not so. Case 2 is the ones, and this is the one that we're addressing. So say for example we have the 4 here, and we need to actually remove the 6 per se. Like, okay, let's say we take out the 6, so remove this and put the 6 over here. Cool. But what you actually notice is that you can't put 6 here per se. It's because when you put 6 here, this 5 just doesn't actually make sense in the tree at all. My argument is this, that usually when you take out a certain value per se, you want to sort of like replace it per se, you want to remove it, it's best to actually remove say the I think I'm gonna try to play it out. I think for the left side is take out the least value per se. So for left side is like we are taking the least value per se, but towards the right side per se, it's more on the highest level of things. So I will try to actually, instead of 6, I'll take 7. So if I put a 7 over here, no, I actually think um, it's the opposite. For here, I'll take the highest value per se. For the right side, I will take the least value per se. And so this one's, I will take a 3. So if 3 is over here, all the left side suppose the rule of the game is that here towards the left is always going to be lesser, towards the right it's always going to be bigger throughout the tree, the subtree, and also not. So if you were to put 3 here, is a 2, cool. 3, 6, cool. Left 5, cool. 6, right, 7, cool. So with that, we're good. And it also proves like the terms for this as well. So when we talk about tree is usually to be on the end of I just feel that it is a hero with no job, right? So it's because I think that the way it maneuver around the map, it's very smart. So it maneuver around the map, it's based on condition based. It's very condition based. So as you can see, like towards the left, it's always the negative. Towards the right, it's always the positive. It's like trying to maneuver around the map based on all these different conditions. I think that's really, really smart. And to actually argue when you actually do a brute force per se, what you really were gonna do is you're gonna just plus this value, check this value, check this value, check this value, check this value. And if you were to see, this is like following the Z operation where you're going through every single element per se. So it would big O of n time complexity. But when you look at the tree per se, like where it is like the Y operation per se, is like log n. You're constantly like trying to actually cut the operation by half per se, whereby say that if you go towards the right per se, you're sort of like removing all this value, and when you move to the right again, you're going to remove. So it's constantly going for a big O or log n, and it's like very similar to previous video per se, where it's talking a lot about like when you have like a balanced tree, you are constantly cutting by half as opposed to operation Z per se. So that's our argument for the brute force. But the main focus is that when you are trying to use casting this using hero tree binary search to actually remove a value, it's gonna be very complicated in the sense that when you that's the key message we want to bring across, is that during this playout series we say that we want to take out a value like say 5. It's gonna be really complicated, and we didn't actually really talk much about how the operation works at, and I believe at the 3/4 of the video it emphasized that a lot. And what makes it really complicated in the sense that, okay, during removing per se, say if we are removing, we're going to go step by step per se. So the first thing first is that if say we want to remove this value, right, and we happen to be able to put this 5 over to here, right, what's gonna actually happen next, that sure we can actually replace the node with 5, but 5 is still, we have like a duplicate node over here per se, and that we need to try to remove it. It's very hard for us to logically go in there and actually remove the node per se, because it's a whole entirety of a tree. So my vague understanding of an explanation will go by this. So we want to try to find 5 per se. Obviously we'll go by the rule book, go right 6, what is our target? 5, so go left. Is it 5? Okay, we found our target. But the thing is this, that we check for if that does it have like say any left child per se. I don't know why you need to check for left child first, but we're just gonna accept it for now. We check for left child, okay, no left child, fine. We're gonna like return to our previous at least, with our right node. So for this case, it's like a null value per se. So it's gonna communicate with 6, saying that okay, here you go, this is the null, and it is gonna draw out the left child to be this item per se, and it's gonna be this null per se, and it eventually communicate back to the new head, which is the 5 per se, and say yeah, just continue what you do. That's what I believe, and obviously there's a bit of a question mark on why they do this and why they need to actually return. Why? Wow, this is obviously driving me crazy. Obviously it involves a lot of like fundamentals per se. I think that it talks a lot about linked lists, because linked lists, it casts a lot of spells to do with say action verb, and I just, in my opinion, like tree, there's a lot of like tree casts a lot of spells with regards to, maybe say, I feel that it's a bit of like casting action verb per se. It's also like constantly returning to previous um, for the value, so that they know where to actually action verb after. That's my opinion. So say that this one is sort of like need to returns to previous per se, like tell them a note for them to actually talk to. And even before that, I don't even know why they check the left node per se, and then just return the right node per se. I don't know why, but there must be some logical reason per se. They return the previous node per se back to the previous, and then they say that okay, I think, to me at least, is that so that this item can action verb to something. This can't be action verb towards the left side with an empty thing. For the left and the right, there must be always something, and for the left per se is in the situation for this one, and it's going to be action verb for this per se. And I think that the main concerns, at least the main agenda that we're very much focused on, is what's with the action verb, what's with the returning of like previous, what's with the checking of the left child, and then returning previous with the right child per se. Yeah, this is annoying and very, very, very concerning to us at least, and this is something that we want to find out in the future episodes. So yeah, not your regular episodes at all, this one's, but yep, everything comes to an end.